Okay, so now let's take a look at the second half of lesson 10.5. We said that there's three ways that chords, or any segment for them, secant or a tangent, can intersect within a circle. So they can intersect right on the circle, and we looked at that ratio, that's x, and then the intercepted arc is 2x. They can intersect inside of the circle, and that's what we did in the last lesson. We said that this angle here, if I call it x, it's going to be x is equal to 1/2 of the two arcs that are intercepted. So I'm not going to go fill all the letters in, but you would add them. So you basically find the average. You add your two arcs, measures, it kind of looks like a face, and then you take half of it. Okay, now we're going to look at the third case scenario, and that's when they intersect outside of the circle. Okay, now we can see up here that there's really, even within that, there's three ways that they can intersect. So here's what we're going to focus on. We can have it so that we have a circle and we have a secant and a tangent. Again, notice the only thing that really matters here is they intersect outside of the circle. Maybe this intersection point is formed by two tangents. And we've actually seen this set up before, but we learned that this to here, to that common endpoint, to the point of tangency, these are congruent. So this is building off of that, but it doesn't pull that into play. But what we see is that if we have two tangents that intersect outside the circle, that's the second case scenario. And the last case scenario is when we have two secants. So again, the key here is not if we have two secants, two tangents, a secant and a tangent. It's just the fact that they intersect outside of the circle. Okay, so that's really all you have to keep in mind. But they need to show you that there's three different ways that could occur. All right, if that's the case, then what you do is it's almost exactly the same as the formula for when they intersected inside, except that now we're going to subtract. Okay, and there are some good visuals that I could show you as to why this works. They just don't correlate well with online stuff. So if that is something you'd like to see as to where did these theorems and formulas come from, I'd be happy to try to talk you through it or show you a little bit more in depth on your own. We can meet together online, okay? But here's what the formula says. So the measure of angle 1, this angle outside, okay, in this case it's going to be the measure of angle 2, and in this case the measure of angle 3. We're talking about that angle formed outside of the circle. It's going to be equal to 1/2 the outer arc rather, minus the inner arc. Same here, the outer arc, which in this case is that major arc, arc PQR, minus the measure of the inner arc, PR. And in this case, that outer arc, measure of arc XY, minus the measure of arc WZ. So it's almost exactly the same. But again, the only difference is that now we are subtracting. So we're not finding the average, if that's how you were thinking of it before. Okay? All right, so to find this, you add up, or you subtract the outer minus the inner arc and divide by 2. Take half of it. Okay? So let's try some. We had done A because it regarded the other theorem. Now let's try letter B here. All right, so they'd like us to find this angle right there, angle C. That's why it's marked x degrees. Now I notice it's formed by a tangent and a secant. That's relatively irrelevant. All that I need to know is that they intersect outside of the circle. So I can say that x degrees, technically, is equal to 1/2 the outer arc, 178, minus the inner arc, 76. So before we calculate that out, let's just revisit it. It's this arc here, 178, minus this arc here, which they defined as 76 degrees, and then we take 1/2 of that, okay? All right, so that said, now we just have to do the easy computing. All right, 178 minus 76, it's going to give me 102, and then I take half of that, and I'm going to get 51. So the value of x equals 51 degrees. Whoops. Okay, all right. I'm trying to write 51 degrees. There we go. Okay, so let's try the next one. Now here, this is formed by two secants. Remember, a secant is just an extended chord, but the only thing that really is critical here is that they intersect outside of the circle. That helps us determine how the relationship with the arcs is going to be playing out. So I'm going to say that 30 degrees, because they actually give us this angle measure here, is equal to 1/2 of the outer arc minus the inner arc. Now my outer arc is an unknown, so it's A. My inner arc is 44. Okay, so in a scenario like this, I think it best if we go ahead, you can distribute 1/2 in. In the last video, we were close to the end and I just went and solved it, but you could distribute 1/2. Some people prefer that, and if that comes to you most smoothly, do it. Some people just like to get rid of the fraction because they don't like dealing with those, so they multiply both sides by 2, because 1/2 times 2 cancels those out. And now I have A minus 44 is equal to 60. I'm going to add 44 to both sides and I get A is equal to 104. So this measure here is 104 degrees. Now obviously if I look at it, that seems realistic. 104 down to 44 down to 30. So I can see how that works. Okay. All right. So let's pause and revisit those if those seem confusing. But we're going to keep moving on so that you don't have a really long video. There is this concept, and we've talked about circumcenter and circumscribed polygons. Now we're going to mention a circumscribed angle. So it's an angle whose sides are tangent to a circle. Okay, so this angle right here, its sides are tangent. That's just clearance stuff as a teacher. Its sides are tangent to the circle. Okay. Sides are tangent to the circle. All right, so the reason that comes into play is because there's this theorem called circumscribed angle theorem. So the measure of a circumscribed angle, the measure of this angle D here, and again, we saw this actually back at the beginning. We said if we have a common endpoint and there's two tangents, the distance from that common point they share to each point of tangency is congruent. This angle here is what they're calling our circumscribed angle. Okay, so this is what we have. This is equal to, the measure of angle D there is equal to 180 minus the measure of the central angle that intercepts the same arc. Whew, lots of stuff going on there. So the measure of angle ADB is equal to 180 minus the measure of angle ACB, this central angle here, okay? Okay, now not to throw too much at everyone, but remember that if we know the central angle, that is the same as that arc that it intercepts. Remember if we go way back, okay, if we have a not way back, but like a couple days, a couple lessons. If we have a central angle, it's that piece of the pie. If I know that this is x degrees and this intercepted arc is also x degrees, okay? So this theorem seems like, wait a minute, we're talking about two tangents, two secants, a tangent and a secant that intersect outside of the circle as we have here. Why are they throwing this new theorem in? Why can't we just do what we did, you know, a moment ago, where we take 1/2 that major arc minus that minor arc and go from there? So I'd like to show you where this theorem comes to play, because there will be times, and the biggest thing I can think of in your short term as to when you'll need these is with SATs. There will be times when that comes in. So you might not always have all the info to use one theorem, and that's why the other one's key. All right, so anyways, let's look at this first scenario. This is that circumscribed angle they're talking about. But for right now, we have two tangents intersecting outside of the circle. If this is y degrees, okay, so this minor arc here, if I put some points in, this minor arc here is y degrees. Think of an expression that would represent this major arc, okay? And if you're having trouble, think about how many degrees are in a circle. 360. So I can say 360 minus y. So I can't say that this arc here that I'm going to highlight is 360 degrees, but I can say that it is 360 minus whatever that piece is. So those are my two expressions. This major arc is 360 minus y. The minor arc here is going to be just y. Okay, so using the theorem where we said if they intersect outside of the circle, like they are here, I can say that x is equal to 1/2 of 360 minus y. Let's put some brackets here. 360 minus y, this expression, minus my inner arc, minus y. Okay, now solving that, 360 minus y is actually just 360 minus 2y. 1/2 of that is actually 180 minus y. Okay, and remember again what y is. Y is this right here. So that brings us to this circumscribed angle theorem, and they phrase it a little differently, but it's essentially the same idea. They're saying this angle here, if I call this x, and if I call this y, now what they're using in their theorem is they're dealing with this central angle, which they call y. But again, this central angle has the same measure of that intercepted arc. But anyways, we can say in short that x is equal to 180 minus y, that central angle, which is the same as that arc. And that's where these two relate to one another. So it's not a new theorem, it's just a different way of looking at it. Okay, and sometimes that's not what we want, but all right, so let's try it out. Find the value of x. If this is a central angle of 135, that means this arc is also 135. But I would just say that x is equal to 180 minus 135. Now, whether you think of it as the angle or whether you think of it as the arc, it's kind of the same thing. So this is going to give me an answer of x equaling 45 degrees. Now this next one, a little bit less straightforward here, and this is why I think sometimes it's easier to think of this as the arc. If this is, and pause it, look at it, but I want to make sure we kind of wrap it up. This is my angle here, so 30 degrees is going to equal 180 minus the central angle. Well, guess what? They don't give me the central angle, nor do they give me the measure of that arc, so I have to look at what they do give me. They do give me an angle that has its vertex on the circle. Well, remember we said if an angle has its vertex on the circle, if that's x, then this arc here is going to be 2x. So that means that this arc here, that intercepted arc, is 2x. So now that means that this central angle has a value of 2x as well. So I can say 180 minus 2x. Subtract 180, I get negative 150 equals negative 2x, so x is equal to 75. Okay? All right, let's try this word problem and see where we stand with that. Okay? So let's read this. It says the Northern Lights, hopefully you've seen those, or maybe you've have intentions of it. I haven't, but I haven't seen them, but I do have intentions of it. I think they seem pretty incredible. But the Northern Lights are bright flashes of colored light between 50 and 200 miles above the Earth. Now, a flash occurs 150 miles above Earth at point C, so it's right there. What is the measure of arc BD? They want this entire arc measure here. The portion of the Earth from which the flash, what is the measure of arc BD, the portion of the Earth from which the flash is visible? So in the Earth's radius is approximately 4,000 miles. All right, so they're giving us a couple of things here. First, let's just decode it. They're giving us that this is the Earth's radius approximately. So that means that this must be a central angle. Okay, so if we can find this angle, we can find this arc, right, measure. All right, next, they give us the distance of the light straight up. So this would be 4,000, but then the light appears 150 miles above. So that entire distance, as they've written in, is 4,150 miles. Now they want us to figure out that light flashes from how far, assuming it's a clear night, how far right and how far left can that be seen? What is that portion of the arc? Looking at it as a two-dimensional figure there. All right, so there's actually a couple ways we can do this. We can use that theorem above. We can pull in some inverse trig. You can try it different ways. Your book goes over options as well, but let's just focus on the right triangle that's formed here. This is a right triangle. So this is 4,000, and what I'm focusing on is this right triangle right there. And this is 4,150. I want this angle, which is this angle. If I can find that, then I can double it to get that central angle. So I'm going to actually, I see that I have my adjacent. I see I have my hypotenuse. That's cosine. Because I want an angle measure, I'm going to use inverse cosine. So cosine inverse of 4,000, which is my adjacent, over my hypotenuse, 4,150. This is going to equal the value of angle BAC. So I'll say measure of angle BAC is equal to this. Okay, now if I calculate that, I'm going to get my answer and double it. Okay, when I double it, I end up getting, I think it's Okay, 31 degrees. All right, good job.